We're recording. Let's go.
All right. So,
Yeah,
uh,
so what we're going to do here today is we're going to do the chapter 5 optimization even though we don't have L3 working because we committed the sin of going directly to the comparing our implementations to the final version of the functions implementations, and they may be assuming that we need to do the optimizations.
yeah. Um, well,
Is
we
that
already
not
have
written anywhere?
what?
No, but the implementations are using lists, so they are assuming the optimizations are done, I guess.
Yes, they are. Um, I think we saw at some point earlier in the book that the final versions of everything are at the end. So I don't remember where though.
Yeah, it doesn't matter. Let's go.
Let's see. Heap representation. I don't think we actually need this, do we? Wait.
I think we're right in doing this.
Are we?
Don't forget to
Doing
pay.
exec. I already did. Memory. Oh yeah, we did this. We definitely did this. Yeah, no. Uh, Actually, yeah, we definitely did that. Um,
Do we need these things here? These constants, lists?
Constants, lists, and anonymous variables. Zero array structures, lists, and variables which appear only once. Um, Sequence of instructions. Unify constant. Set constant.
Like to introduce this, we're gonna have to change the parser
Why?
because the parser doesn't know what is a con.
But this is only adding special support for structures with no contents, atoms essentially.
Hmm. So I guess you could say that this is like a pre-processing step, maybe.
Why? I don't think we need to change anything. This is mostly for code gen. And I guess there would be a change in the evaluator as well, actually.
Oh, I see. We're actually the code generation checks if the font trace has zero arity, I guess.
Yeah.
Ah, that works.
Uh,
Do you need this though?
mm, Maybe because this might affect unify variable and friends.
I doubt it, but let's see the implementation.
Mm, Put structure Set variable and unify variable get structure. That would become unify constant, and this would become set constant. Uh,
Yeah, so far these are just optimizations. Like optimizations that don't seem to touch like syntax sugar, essentially. Well, not syntax, but code generation sugar, I guess.
hmm,
Yeah, I think we don't have any of those four currently.
put constant, get constant, set constant, unify constant. Programming with linear lists, blah blah blah. Non-empty list functors. Yeah, these are the new instructions
Put
and
list,
functions
get
for
list.
lists. Put list and get list. Mm,
Yeah, this seems fine.
yeah, I don't think we technically need this.
Like everywhere else in the code that assumes these constants we're not doing, which is the unify.
Mm, then this is
Set
for single.
void and unify void.
This is for single occurrence variables in non-argument positions.
We have that in the triangular example. That's the. Actually, no. In the example precisely, we don't have this, I think.
This would only be needed if we actually wanted to discard a value, which the triangular numbers example doesn't do ever.
Yeah, but does this matter for like. This may be related to the other instructions, you know?
Hmm. An anonymous variable occurring as an argument of the head of a clause can be simply ignored. Yeah, this shouldn't affect. Yeah, we don't need these either, and this shouldn't affect what we're doing. A note on set instructions. Defining the simplistic language L0 has allowed us to introduce, independently of other prologue considerations, all WEM instructions while dealing with unification. Yeah, here are the other two. Strictly speaking, the set instructions we have defined are not part of the WEM as described in either of those two papers. Uh, There, one will find that the corresponding unifying instructions are systematically used where we use set instructions. The reason is, as the reader may have already noticed, that indeed this is possible provided that the put structure and put list instructions set mode to write. then clearly all set instructions are equivalent to unify instructions in write mode.
Is that true?
Well, yes, it should be.
Can we check the code on that?
We can check the code on that. That's probably a good idea. Evaluator, set.
Put structure.
Mm, put structure.
That's
Mm, well, it doesn't, but then we do have the set instructions, so
no, but go back to the book. But that's not true though. Put
what do you
structure
mean?
does not put the mode into write.
It
Like,
doesn't because we're not using unify to we are using set after put.
oh, so he's talking about the previous implementation of put structure, I guess.
He's talking about the implementation of put structure in the papers, which apparently is different than the one in the book.
We chose to keep these separate as using set instructions after put instructions is more efficient and makes the codes more perspicuous. Moreover, these instructions are more natural, easier to explain and motivate as a data building phase of unification before matching work comes into play. Accidentally, these instructions together with their unify homologs make on-the-fly copying part of unification, resulting in improved space and time consumption.
Mm,
I don't know if I understood what he meant by set instructions are equivalent to unification.
they are only equivalent if we are in write mode. If we're in read mode, they are different actually.
Can you check that? Can you go to the code?
Sure.
Set variable, for example, is not doing unify at all.
No, no, no. That's not what that section of the book is saying. That section of the book is saying set variable is equivalent to unify variable if we are in write mode.
I don't understand how someone can say that. I'm not seeing the code.
Uh, set variable. Right. So in write mode, we make a reference. Then we put the reference at the position of the age register.
Mm-hmm. Hello, Maggot.
Then we update the store, the age register, and the S register in one but not the other. Is that a problem? It might be actually.
Oh yeah, but let's wait, right? Maybe further on the chapter we're gonna actually change more stuff.
Hello, Magetta.
Hello. What are you
Wait,
guys
but you
doing?
come. Hello, Maggot. How are you doing, man?
I have a story to tell today.
Yeah, but
But
we are
anyway,
recording this time, so.
yeah, I'll tell later.
Yeah, the only difference between them is the S register, right, Marinho?
Yeah,
Pretty much.
pretty much. Is that a
Uh,
problem though? It might be.
no, but again, we should go back to the book and keep scrolling.
Register allocation. Hmm.
Oh, this is to remove the no ops.
Yeah.
I don't think we need this. Do you think so?
There's clearly no need to allocate register blah blah blah. Not at this point, no.
So let's keep going. Yep, get variable input value. Yep, exactly.
Mm, this we already did, right?
We should double check.
Yeah, we changed deallocate um, to
Yeah, I think it's
update the
doing this.
CP register instead of P, and we have execute. Chain rules, generic translation of a chain rule of this form. Um, allocate n, get arguments, put arguments. LCO turns that into this,
Makes
which is already
sense.
the case. But that can actually be optimized into this, apparently.
Oh,
Get
we
argument.
already attempted this before.
I don't think we did this actually.
I think we did, yes. We
No,
changed the cogeneration to remove the allocates and replace them with executes, but that didn't work.
no. We did this. We didn't do this.
Mm, oh yeah, no, I think you're right. I think we removed the proceed with the allocate actually. Maybe.
Hello, John.
Hello.
Uh, yeah, but this doesn't change the semantics of any other instruction. It's just code generation optimization. So environment streaming. Um,
Mhm.
hmm. Each permanent variable in the environment can be associated with the goal in which it is used last, and therefore can be safely disposed of before performing the call. The intended effect of such a process is to make the current environment frame size on the stack shrink gradually until it eventually vanishes altogether by LCO. We're not doing this, but also this shouldn't. The call instruction is given a second argument counting the number of variables still needed in the environment after the point of call. Actually, I remember seeing something like this when I was looking at the bean instructions.
That's cool. Yeah, but it seems that this is related to what the heck we're doing though, because this is changing the stack and so on.
Yeah, this is changing. This is changing allocate, I think. In order to reflect the correct value at all times, the offset that it gets from the preceding environment must be updated by each streaming call. In fact, such updates are not needed, since a more precise environment stack offsets now explicitly passes an argument to calls. Are they? Alright, they are. The argument of allocate becomes superfluous, and it can be dynamically retrieved by allocate as a consequence of the following fact.
I have another question, Marie.
Sure.
Let's assume for a moment let's assume for a moment that the code at the end of the book is the one already with the optimizations. If the code that we have is that one, even though we didn't read it when we should, uh, they should be correct anyway, no?
No, because we didn't actually use all of the instructions from the end of the book, just the ones that we were missing at the time.
I don't think that's true.
It is, because allocate still takes an argument.
But, okay, let's go to the end of the book on allocate then. We already checked this before. I think I did
We
a,
didn't.
like a list. No, I think we did offline a list of all the functions there. But we can double check. Let's double check.
The now definitive definition of allocate is allocate with no arguments. Allocate with no arguments.
So let's do that. I can help you with the allocate.
If E is greater than B,
That is inside the new stack pointer function.
it's a new stack pointer. That is true. New E plus code at -1 plus 2.
Well, actually, you are right. Apparently, we didn't do the checkup on all of them. We only did checkups on unify functions. I think put functions and get functions, maybe. Okay, but apparently the math is different now, hey?
It is because we're retrieving the size of the environment from somewhere else.
Yeah, but again, I think we should all read chapter 5. But if the code that we have on the bottom there, just to make it work, if our implementation is equivalent to that code down there, we are already going to have all of the optimizations aside from constants and lists, right?
Right. Hmm. Actually, since we are not actually doing environment streaming at all, we didn't touch the call instruction. So,
Did we touch the call instruction? I have
well,
no
no.
recollection anymore.
This just takes the functor argument. It does not take the number of permanent variables after the call.
Okay, so
So
your
actually,
hypothesis is that because we're not changing call, we don't need to change allocate.
yes.
But we did change the allocate, right? But I guess what you're saying is it doesn't matter, right?
But we changed the allocate because we needed to for proper tail calls. This has nothing to do with environment streaming.
Okay, that's good.
Stack variables. Environment streaming code.
Yeah, but the problem that I'm having is we may not have examples because the examples are cumulative. So they are already doing the environment trimming and we were not. Yeah, the put variable. No, down there.
Down
Are we
here.
doing this implementation of put variable? I have a feeling we are. Because
When
this is
used on
for
a
permanent variable, permanent register, right? Yep,
if it's a Y register,
we are doing all of this.
E register plus Y register plus 3.
Why the plus 3?
Well, I know there's an extra 1 here because we're doing 0 based and the book is 1 based, but that still puts us 1 less. Oh, I guess it's because since we're not doing environment streaming, we need to keep track of how many permanent variables we have, which takes an extra stack slot. So
Damn.
that actually makes sense. Reference, we make a reference, and then we put the reference at that address. This is putting it directly on the stack, but that's what we're doing though. And then, yeah, we're already doing this. Unfortunately, there are rather insidious consequences to this apparently innocuous change as it interferes with environment streaming and LCO. Um, well, we're not doing environment streaming, so that's fine. The trouble is that environment variables may be disposed of while still unbound. Therefore, any reference to an unbound stack variable runs the risk of potential catastrophe.
Wait, isn't that what we're doing? Becoming a dangling reference upon careless discarding of the variable? Isn't that exactly what is going on? We have a dangling reference, and that's why we're having a free variable, right?
Hmm, it is no longer correct to let the bind operation set an arbitrary direction when establishing a reference between two unbound variables. More pathologically, the following instructions have now become incorrect if used blindly in some situations. Put value and set value does also unify value in write mode.
Linkage
So
problem. First giving a correct binding convention, then analyzing what may go wrong with put value, and reset value and unify value explaining how to repair the trouble. Man, am I wrong on saying this? We have a dangling reference, right?
this might be what we need, yes.
That's kind of funny. The author said himself, if you're not careful, you're gonna have a problem, which we had. So interesting.
Variable binding and memory layout. Three cases of variable bindings are possible, from heap to heap, stack to stack, and heap to stack. In case 1, when the bind operation is performed on two unbound heap addresses, which of the two is made to reference the other does not affect correctness. However, making an arbitrary choice does affect performance, as it may lead to much more work than necessary by causing more variable trailing and resetting than may be needed. Uh, yeah, I think the basic implementation of bind already deals with this.
Now let's see.
In cases 2 and 3, the symptoms are quite more serious, as which direction the binding occurs can be incorrect due to potential discarding of stack variables. For
Interesting.
example, the rule P of xx given by Q of x and R of x invoked with this query will not work correctly if y is bound to x, since Q1 may leave the stack variable x unbound. The other direction is the only correct one. Right, because this y will be allocated first on the heap as part of the query, and then these x's are bound when we enter the rule. As it turns out, most correct bindings can be ensured by following a simple chronological reference rule. Always make the variable of higher address reference that of lower address. In other words, an older, less recently created variable cannot reference a younger, more recently created variable. Okay, that makes sense, I guess.
But are we doing that? Because I kept scrolling down on this, on these observations, and he's not providing any new code for them. So I wonder if this must be done by us ourselves.
I mean, we can check. This is the stack, right? And this is memory. Put structure, put value. Put value. Call triangle 3, blah blah blah. And reachable get structure, of course.
Yeah, this is the problem that we had when we introduced tail calls. So we do a get structure and we go to an unreachable, which is kind of weird.
That's not. I pressed twice. 1, 2, 3, 4, 5, 6, 7, 8.
It's here.
S.
Okay, so the older can't reference the newer. For let me check
Okay,
what
we
is
have a
the
bunch of
value.
addresses for the backtracking. We have a structure, two structure, a reference. Those all point to the heap, which is fine. And then we're preparing the arguments for this call. And we break on the next instruction, so we
Okay,
can't
it
see
isn't.
anything
Okay,
here.
he did change the code though. But it is
Okay,
written in English instead of having it in the code.
what do you mean?
Yeah, so he provides two new functions called put unsafe value and put and I think set local variable, let local value, and you need to do the ifs yourself, I think. But maybe I'm jumping to too many steps. We should continue reading that. But anyway, let's go back to what you were doing before.
Right. In case 2, binding rule 1 is also clearly beneficial for the same reasons as for case 1. It happens to also be consistent with the ordering among variables within a single environment, set up to allow environment streaming, which we're not doing, which might be a problem. This is all the better. Unfortunately, this rule is not sufficient to prevent dangling references in a stack-stack binding, as we'll be seeing in the next subsection. In case 3, the problem is that stack space is volatile while heap space is persistent, making references to the stack potentially dangerous. Clearly, it would be a source of complication ever to establish a binding from the heap toward the stack, whereas the contrary presents no problem. Therefore, the WAM enforces the following. Heap variables must never be set to be a reference into the stack. To suit this, the WAM organizes its memory layout specifically so that when binding rule 1 is naturally consistent with binding rule 3, the stack must be allocated at higher
Yeah, but
addresses than the heap.
we are doing that.
We are doing that, yes.
But are we doing number two though? Heap variables must never be set to a reference into the stack. That's very easy to check, right?
Well, it is. Well, so far, all of these variables in the heap point to earlier in the heap, so we're safe, I guess.
Yeah. Okay, let's continue there.
Uh, A reference chain containing any stack variables at all will have them all appear contiguously and early in the chain.
Wait. Let's put this example there. This p unsafe code. Let's see what happens.
allocate get variable from a1 to y1
No, I mean in our
with
stuff.
in our stuff.
Yeah, make a L3 L no. Yeah, L3 true or something. Dot Karuta, and let's actually put that into the compiler and see the code generation.
Okay. P of x,
I can help you with this. Body,
qyx, and ryx.
yeah, it's basically Q and then R immediately after that. We need a query, I believe. Do we?
Um,
Maybe we don't. In debug mode, we can just inspect whatever is there.
we need those just so those references are defined.
Let's change the main.ml and let's run
And let's
and
do
see the code.
P of, I don't know,
And we're not
A.
doing the environment trimming, so we need to be careful about the allocate having an argument.
Main. Uh,
Okay, this is good. But this is not doing what we want though. Oh, this is already wrong.
uh, let's see.
This is wrong. Immediately.
One moment.
Oh wait, did you add the query? I didn't see.
I did, but there's no debug, so no breakpoint.
No, but that
Actually,
doesn't
let's do
matter.
that.
No, but we can ignore set variable in the call there. Okay, so it's allocate, get variable, put variable, allocate,
P
get
prints the
variable.
mach. Do we have a helper for the code? We
No,
do actually. There we
oh
go.
yes, but we don't. I didn't make the helper yet for the debugger. Yeah, no, but uh, we don't need the debug, man. We can just jump the first two instructions, and then everything. The previous print that you had was easier to read.
Okay. Um, Q2 is at 16, so this is
Get variable, put variable. Yeah, so correct so far. Put
execute
value.
R is the end.
This is correct. And then call. Wait, this is wrong. Oh no, the call is in the middle there. Take that back. Put variable, put value, call to queue. Then we do put value again. Yes. Deallocate, and then execute. Yeah, that highlighted piece of code is correct according to this example, which is unsafe.
A1 to Y1, A1 to Y2.
We are
Put
generating the
value.
unsafe one. Pretty much.
Yeah.
So maybe that's the problem. Man, can you scroll down a little bit? And can you go to the evaluator and let me see the implementation of put value? I have a theory, but let's read the book. If my theory is right, I'm gonna rant.
Uh, we see next that this rule is violated by some instructions. We presently examine this and adapt the design so that no incorrect binding may ever occur. A stack variable is discarded before calling the goal in which it last occurs, although it may still be unbound or bound to another unbound permanent variable in the same current environment, one which is to be also disposed of. Clearly, the danger is then that the call may refer to the discarded variables. For this reason, a permanent variable which is initialized by a put variable is called an unsafe variable, which first occurs as the argument of a body goal, which is the case here,
Ah,
right?
holy fuck. Actually, I got it. Okay, so put unsafe value is a new is something that we're gonna wait. How are we gonna implement that? Anyway, continue reading. What the fuck, man?
Let us take an example with the rule, that's the one we just
Man,
wrote.
pause.
Okay,
There is a section called nested stack references.
okay.
You gotta be fucking kidding me, man. We wasted all of that time and got frustrated because we didn't read it. Holy fuck. Go on. No, no, no. Let's continue this one. Let's implement this also.
This is because y is initialized with a put variable since its first occurrence is in a body goal, while x, first occurring in the head, is initialized with a get variable. Figure shows the incorrect translation as it is done in our current setting. Yeah, I think that's precisely the problem actually. Because like if we go to triangular, new accumulator is introduced in the body of triangle.
That's true. So it's
So
unsafe. Is that what you what? But I thought that what making it safe was to put it on the stack because it's permanent, right?
no, that's not the problem. The problem is that it's a stack variable that's being initialized by a put variable.
Sure.
That's what makes it unsafe.
Wait, could you go back to the book? I don't think I got what is the unsafeness because it may refer to the discarded variables. But again, variables that are put on the stack are not discarded. What do you mean? Uh, let's take an example with this rule, which in both x and y are permanent variables, but only y is unsafe. This is because y is initialized via a put variable, since it's while x first occurring is initialized with a get variable. Figure shows the incorrect translation as it is done in our current setting. Let us trace what happens when put value this is used on line 5. Let's assume that p is called with an unbound variable, that is, with a sequence of the form. Boom. Thus, at the point right before line 0, A1 points to the heap address, with an unbound ref cell at the top of the heap. Then allocates creates an environment on the stack. Line 1 sets a stack to this and line 2 to this. Line 3, blah blah blah. Line 5 would set A1 and line 6 sets A2 to this. Next, the allocate throws away stack 77 and stack 78. Suppose now that the code for R starts with an allocate reusing stack space. The get instructions of R will find nonsensical data in A1. I don't know if I got it, man. Could you try to help me here?
Allocate creates an environment on the stack where y1 is address 77, y2 is 78. Then line 1, which is this one, right?
Yeah, what
Of
is
course, this
again?
is zero based.
Yeah, but yeah, of course. But let's what is the semantics of get variable and put variable? I think that's what I need to remember myself.
They are both used to initialize new variables that are appearing for the first time, but get variable is
Temporary and the
used
put is
for
permanent.
no, that's not it at all. Get variable is used when you are initializing the arguments
Ah, that makes sense.
because the arguments are given from a previous environment from before the call, right? So they are already initialized.
Okay, so the put variable being introducing something for the first time because it's in the body, right?
Yes.
Whatever we are doing, we are deallocating that shit.
Uh, yeah.
Okay, let's go. So that's the fix. Let's try that. He just said that we can check this at runtime. That an unsafe variable binding can easily be checked at runtime, so that trouble may be averted on the fly by taking appropriate measures only if needed. Let us reflect on the possible situations of a given unsafe variable in the last goal where it occurs. There are two cases that will need attention: when it appears only as an argument of its last goal, and when it appears in the goal nested in a structure, whether or not it is also an argument. We will treat, we treat later the second case, as it interacts with a more general source of unsafety that we shall analyze after treating the first case. So let us consider for now the case where all occurrences of the unsafe are arguments of the last goal where this appears. Are arguments of the last goal. All these correspond to put value instructions. As explained, it is desirable to ensure that a runtime check may be carried out, verifying that no reference chain leading to it eventually points to an unbound slot in the environment. The solution is to use a modification of the effect to ascertain this. More specifically, let's call this modify instruction put unsafe value. It behaves exactly like that if the reference chain from y does not lead to an unbound variable. Otherwise, this altered instruction binds the reference stack variable to a new unbound ref cell pushed on the heap and sets AI to point to the cell. So he did what I this is stupid. So he created a safe version, but he called it unsafe. What the fuck? Did you get this, money?
Yes.
So this is the version that we need to have implemented. This is the real put value.
Mm,
Like, why can't we just do this all the time? Because if you scroll up again, actually it's up or down. Let me see. It's down. If you scroll down, see here. No, 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 there. If the safety check is done last, as in boom, notice that he's making a difference between put value and put unsafe value. Why?
because one instruction does more work than the other.
Nah, we don't care about that. So that's it, man. This is a problem, right? We just checked that our generated code does have this problem. So we just need to implement this version that is doing the check for the, well, doing the check that he just explained, checking for the unbound stuff.
Mm,
Like later we can optimize this to make it like actually generate code uh, that that will be more efficient. Is gonna do exactly what it needs instead of doing all the time.
put unsafe value if address.
I think what we're doing is only the begin and end. That's what the current code does. The deref and the if are the new things. Can you check that? Can you go to put value?
One moment.
Not even. Not even that is doing.
Mm,
This is not the same thing. So page 81, let me check.
if index. Hmm.
Yeah, this is completely not okay.
Yeah, put value is definitely wrong.
Yeah, we should definitely fix that. Let me check the final version of the code here for a bit, just to make sure we are doing fix. Yeah, man. Yeah, this is completely fucked. I have no idea. I have no idea why. This is so unintuitive. Why he made the complete version with the unsafe name? That doesn't make sense.
But they are both used lemos.
No, I'm not denying that. It's probably because of what you said. He's doing the distinction between put value and put unsafe value because one of them does more stuff. Fine. Why is not called put safe value if that's actually the safe one?
No, no, no. The instruction is safe because the value is unsafe.
Yeah, exactly. I guess what you're trying to say is that he would name this put value safely. Like, damn, it's so weird. Anyway, are we going to implement this version? Because looking at the final version of the code here at the bottom, that's it. We are doing exactly what put value should be doing. But in my opinion, if we're not going to be doing the differentiation that he's doing, we should always be doing put unsafe value. Or
Mm,
am I wrong? Actually, if you think about it, they are substantially different. Maybe you cannot just replace it. You need to do this. Which means that you're going to have to detect if something is unsafe. Hmm. What do you think?
give me a second.
Oh, there is a
Mm.
paragraph about that. The question still remaining is to decide which among several occurrences of put value must be replaced with a safety check modification for a given unsafe. In fact, it is sufficient to replace only one of them, although not an arbitrary one, but quite importantly the first occurrence in the last go. To see this is an example, consider this clause. If the safety check is done last, as in this, the argument register will still contain a reference to the discarded environment, where R2 is called. Therefore, the following is the only possible correct code. It has the effect of globalizing the value of y1 so as to guarantee that it may be discarded without leaving a nonsensical reference in one. That Okay, so we need to be able to detect if it's the first occurrence in the last go.
The
How
first
are we
occurrence in
planning
the
on doing
last
this?
goal that uses it, to be more precise.
Yeah, how are we planning on doing that? Are we gonna actually? There's another question. This must mean that we need to have a second pass compiler now, like a two pass, like a three pass or whatever. Because
Why?
now we have pre-processing, We have the actual compiling process, and then we're going to have to do a post-processing to
Why?
replace the first occurrence of the last goal with this.
Do we?
Well, what are the other available options?
Well, we need to check when we're emitting the code for each call in the body of the predicate. Um, we need to check if the each permanent variable that we are using is used in any later goal. If they are not, then we know this
Isn't
is
it
the last one.
easier? Wait, sorry to interrupt you. Isn't it easier to just have like uh, basically a backpatching strategy again, but when we emit the first put value on a part for a particular goal on the last on the first occurrence on the last goal, we
That
save
will
that, and after it's done, we backpatch it.
but the logic that we need to do to save that is the same logic that we need to do to detect if if we need to emit the different instruction or not to begin with.
I don't get it.
Okay, which criterion are you going to use to decide if you're going to save the address to backpatch it later?
If it's the first occurrence, if it's the first occurrence.
And if it's the first occurrence, then you can just emit the correct instruction to begin with.
Mm. Yeah, but that's the thing. We don't have a semantics in the code generation for first.
Well, we need to introduce another set then.
Okay, I can buy that.
Uh,
But then
Let
this
me
is
think.
huge, huge. This is not optimization.
Mm,
Well, I guess it depends on how you put it because this is an implication of tail calls and environment trimming, right?
yeah,
Okay, so this is optimization, but like a we have the tail calls.
we do.
Yeah, but that doesn't make sense because when we didn't have the tail calls, we wouldn't have to do this, right?
But we are still using this weird implementation of put value that's kind of weird though, which is just set value basically.
No, no, no. But the put value implementation is gonna stay anyway. Like, as
Mm,
far as I can tell, if you don't have tail calls and you don't have environment trimming, all of these 5.8s are useless because they don't will never happen.
hmm.
So there is still some mystery on what the fuck happened that was not working, just not working.
Hmm.
Yeah, but let's implement this then because we do have tail calls. Or are we willing to undo tail calls? Because that's also easy, right? I think it's just reverting one commit.
Mm, let's see.
Let me also read that again to see if I'm not saying bullshit. That this is a consequence of environment trimming and tail calls. Yeah, this this thing is a problem that appears if you do the put variable for permanent registers and you're doing environment trimming and tail calls.
Um, Actually, it's also a consequence of having stack variables standalone.
That's not what it said here, but okay. He's not saying any of that. That if you have stack variables, well, which you're gonna have.
No, stack variables, I mean, like it's a free variable that only exists on the stack. It's not a free variable on the heap that's referenced by a bound variable on the stack. That's different.
But do we have stack variables?
We do.
Like, aren't those the permanent variables?
Yes, but like the naive approach that we were doing like way before we started looking at those actually the code was still broken back then though.
No, but it's pretty much hard to tell. Like but again, I can't. It's hard to tell because back then we may have some mixes with the final code at the bottom. Doesn't really matter.
Mm,
Actually, that's another option, Marin. We can go back to chapter 4 and backwards and redo the implementations of the naive functions and just like forget the end of the book. That's an option as well. And undo tail calls because that's the only optimization that we have right now. And the put variable of
it's
permanent registers.
hmm.
But that's an option. If you don't want to go, we don't want to go through this to guarantee that we're not doing bullshit. We, but that's the thing. I think there's a chance it's not gonna work at the end as well, and then we're gonna be very pissed about that.
Uh,
Yeah, but again,
mm,
we which path do you want to go with? Because if we're going to go backwards, we cannot trust any of the bottom. Like any of these things, any of those functions in here, we can't trust them. We're gonna have to like go one by one, checking what is the latest before chapter 5, essentially.
uh, which value? Oops. Takes a register and an A register. You know, there's one thing that I'm not sure. Takes a register, takes an A register. Mm, yeah, put value is the same, both there and here, actually.
Oh no, yeah, but we're gonna have to do that treatment to all functions. Unify, for example. the unify that we first saw in the book and the unify on the bottom, they are significantly different. So you had to go over all of these functions one by one and get the latest before chapter 5 and see if they match. And if they match, we try and see what happens.
Yes, that's an option.
Oh, but there's also the option of just go with it, like just implementing this problem that we're currently having.
Mm, X and A. Wait, let's get variable. Put value. Put value takes an X and an argument. Oh, it can be a Y register as well. Takes a register, takes an A register, and then does a set register. If index of register is less than the size, then wait, this is get register, not set.
So what
Hmm,
do we want to do?
I think I want to keep going actually.
Okay, so we're going to implement put in safe.
Yes.
Okay, so let's do that. Now let's start by going to the code generator and doing a grep on put value instruction. And we're going to have to introduce a put unsafe value instruction.
Mm, hmm. Address equals dref, which
I'll be
is
back.
what we do here. Actually, we do that earlier. If address less than E, hmm. 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 Are we doing a deref here? We're not actually.
I'm back.
Hello,
So,
welcome back.
did you start the code generation?
Hmm. Actually, I'm thinking maybe if address less than e, that takes a dereference. That takes a dereference, which we're not doing at all. I'm thinking I'm actually just going to put this inside of set register temporarily and see if that helps first before I mess around with the code gen.
Mate, so you want to combine put and save value in set register?
Well, yes.
How are you planning on doing that?
Well, this goes inside of the branch that deals with permanent registers.
Okay, that sounds like
This,
a gamble to me, but okay.
no. This is what we're already doing, Lemus.
I agree. I noticed that. Okay, so let's gamble. Uh, let's do it.
Mm, so first of all, we need to dereference the value of the
Oh,
cell.
okay, but that's gonna be fucked. So you need to grab the deref implementation and put above this. Yeah, put all the way up. All like yeah. Okay, now we can use it. Let's go. So then you do let addr.
Problem is that this takes a raw address, right? Just an integer.
No, but this is what we're gonna do anyway. In the book, it's saying that the integer is e register plus n plus one.
No, that's the address that we're dereferencing.
Yeah, which is the use case of this function.
No, this is the address that we are dereferencing. We already have this as the cell in the set register.
We already have this in the cell. Um, I don't get it. What do you mean?
Like this thing, right? Inside of the deref actually comes from put value. Actually comes from this get register, which we do before we call the set register, and it comes from here actually.
But how do you know that this is the dereference of e plus n plus one?
Because here,
Because of that. Wait a moment. Ah, sorry. Ah. How do you know that this is the same as the deref on that stuff, man? I'm not following the math.
no. This is not the deref. This is what's inside of the parentheses here.
E plus n plus one. But we're doing
Well,
plus two well,
I
but
guess you
that
could, I guess you could say this is one layer of derefing.
What? Uh, Wait, but you're saying that this entire stack get is that number.
This entire stack get is like, you know how dref calls itself recursively until it can't anymore?
Mm-hmm.
This is basically calling dref once and only once without the recursion.
Oh, so your plan is to keep going, essentially.
Yeah.
Man, that's I don't know if that's a lot of. Okay, I'm gonna trust you, Marinho. You have a lot, shitloads more of more understanding than I do. So let's follow your gut.
The problem is that this can be any one of these actually.
Yeah, we're gonna do a get ref, well, get address or something that the pattern matches structure references addresses, extract everything out
Uh,
of it, and then errors out if it's not.
Actually, if it's a reference, we need to do deref. If it's a structure, this is already as deref as it can possibly be, and everything else would be an error actually.
So let's make the ref cell. Let's make a variant of the ref, and let's call it the ref cell. And this is gonna be to have to be an AND, I think, because this is gonna be no mutually recursive actually.
Mhm.
The ref cell that receives a cell. Well, I mean, you can do pattern matching here, right? Because you only have one argument, or you have two arguments. That's true, actually. No, sorry.
This returns an address. Should we return a cell
Man,
instead? We
man,
probably should.
man, but look at line 7.
Line 7.
Aren't we already doing like the check on a cell?
No, no, no.
Oh,
This.
but it is on the first argument that we're doing. I see. 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 Okay, you do pattern matching now.
Mm, yeah, this actually should return a cell.t.
I wonder why, but okay. Doesn't make
It
sense to
should
me.
return a cell.t. Although,
Why a cell.c?
if it's a reference of value, when value is different from a, we keep going. Otherwise, we just return a. Because we're going to put this back inside of a register, right? And registers take cell contents, basically.
I'm gonna put this back inside of a register. Okay, that's a good argument.
Uh, so match cell with, if it's a reference of another with an address, then
We deref the address and put back into a reference.
we need to deref and put it back into a reference. Is that sufficient?
Well, actually, I'm a little, I'm a little confused because if we're gonna deref the number in here, we're not gonna have a reference, right? Because deref only stops if you don't have a reference.
It actually also stops if you have a reference that points to itself, because that's how you represent a free variable.
Yeah, but let's say that that's not the case. Let's say that you're actually going to line 10, right? Shouldn't you just do a story.get? on the deref result. I think that's what we should do actually. Yeah, and then we can do an R pattern to do with this with all of them that are not errors. You know what I'm talking about?
That doesn't work if the reference. Hmm.
No, we're gonna just do a star.get like line 7, but that's gonna be the result. And we're gonna use instead of A, we're gonna be using the address of the cell. Well, sorry, the dereference version of the address of the cell.
That doesn't work if we are using the address of a structure.
Then, but should structure zero out?
No, they shouldn't.
Okay, but then we could just make another branch.
Uh, we just return the cell in this case. Um, fail with unreachable deref cell, and then
And
this one.
this is just a store get on the store using the deref of the address, isn't it?
Let's see. The reference will always point to somewhere else on the heap. It may point to a. Can it point to a functor though? Can it point to a functor? It may have to actually.
I don't remember seeing any of that. I think we always had the structure instead of a functor.
Hmm.
But don't quote me on that.
Actually, no. If we have a free variable on the heap and we unify it with a structure, it should become a structure, shouldn't it? If it's free originally.
I guess.
Unify. Yeah, if one or the other is a reference, we do a bind.
Yeah, we just do get store gets there.
Hmm.
I don't think that's correct.
Hmm. Store get. This takes the store first, right?
Yeah. Yeah, this won't compile
Deref
of address.
address store.
And the reason this won't compile is because the reference there is wrong. This
This
is just the
expression
store.get.
has just a store.get, right? Because this is already a thing.
No parentheses needed in there, by the way. Oh, thank you. Thank you for Mate. That's it. That's it. So now we do what you wanted, which is let address equals deref cell, and you pass the cell that you're getting on line 18. You pass that to it.
Hmm.
ADDR cell, I guess.
Deref cell of
Cell
the cell and the store
in.
in
That will give
um,
you pattern matching on that.
match deref cell with
So what are you
um,
expecting here?
if it's a reference with an address
And when
when
the address
the
is less than the E register,
address is less than the E register,
then we do all of these things that we have there,
we we do what we're already doing in this case.
which is still some I don't know. I feel so uncomfortable that we are mixing two things that are completely. Oh, they are. I guess they are related, but not the way that the book is explaining it. And if it's anything else, we need to do something else, completely different.
If it's anything else, then
Let reference. We're gonna do create the reference first.
actually this is not quite right. If it's an address, and then if it's anything else, if it's anything else, um, actually that's not quite right. If it's a reference of anything else, then we do the else here, and then actually that's not quite right either because hmm,
Man, can you go back? I'm starting to question this approach because we are doing if the address is less than the E register, the book says put into the AI register the store using addresses and index. We are
that's what
100% not doing that.
that's exactly what we're doing right here.
How? When? Like where the heck is written E register plus 3? Well, I guess plus 2 because of the plus 1 plus index of register. Where is that
Right,
written?
it's right here, Lemos.
No, no, no. I didn't. My question. I didn't ask that. I asked where is that written in the book? I only see that line there on the then. You see?
Oh, this is actually putting this in the A register on the right here.
Yeah. That's what I said. Well, that's what I meant when I said we are mixing two things that seem completely unrelated. I think you got bamboozled because you saw we
Mm,
reading from the stack and putting into a register and thought, okay, this is what set register does.
mm,
Which, well, in the case of put value, it may be, but that seems like a coincidence to me. Yeah, in this case it would work because the register being set is the A register. But the value that we're setting there is wrong because it should be store
yeah, we
using.
should actually put those things down here, I think. Let's do that. This goes here.
Wait, so are we gonna combine put value and put unsafe value? Is that the plan?
Yeah, that was the idea I had. It's just I figured we could just change this, but I was wrong.
Wait, uh, I think the first thing we gotta do is pattern match, do some sort of pattern match on the register, man. Before value even. Because if it's a temporary register, we do this, right? We do we do whatever this does. If it's a permanent, then we do the stuff in the book. Am I right?
Put unsafe value with a Y register.
Yeah,
Does
the
this.
the put value on the bottom of the book does vn, not yn. And as far as I know, v stands for anything that is x or a.
Or Y, actually.
Whoa, so the previous put value behavior is also applicable to permanent registers.
Why would it not be?
Okay, but then I don't see how we can combine them then. We need to make them separate as far as I can tell. What is your vision to combine them? How are you gonna
Uh,
detect?
Okay, basically the idea is to do something like this. Match register with, actually, do we have a helper for that?
To do what?
To check if a register is permanent or not. I don't recall.
Uh, Wait. What do you, oh yeah, no, this is just pattern matching on them.
If it's a Y register, then if it's a Y register, then we do something. Otherwise, if it's an X register, and we do what we're already doing.
I think the if needs to go in that branch of the Y register, right? Maybe. I'm still not getting how I'm gonna detect between this and the original put value for permanent.
Hmm, let's see, this is doing a deref, and then that means we need to do another match with, do we? No, we have deref cell for that. Let deref cell equals deref cell value in,
You're missing the store there, bud.
right, so we do
Which
need this
which you're gonna have to get from computer.store. That's way easier. Thank you.
in. Um, Match deref cell with, if it's a reference, with an address when address is less than computer.eregister. In that case, we're in this branch. So
Which essentially means set register of a register using a store.get.
set register of a register,
The at or parentheses
store
store
get,
get. I forgot the order, but something like that.
takes the
You
store and the address. So store computer.store address.
pretty much. Yeah, that's it. Okay, so
If it's a
how?
reference,
Okay.
but we're not in that case, then we have to do this.
Yeah, but put parentheses in this and let's do the catch-all. The catch-all is the set register below.
And the catch-all is this.
I have no clue if that's gonna do it, but I trust your instincts, Marie. Okay, so let's write this version then. So the first thing we're gonna do is the let ref. Well, let reference equals inside that parentheses there.
Uh, right.
Let
So
reference. Let reference.
one moment. We need to, right. We need to do a let reference. Don't we have? I'm pretty sure we have a helper for that already, though.
I think that's
Let reference.
yeah. That's this is not a helper. That's just a line. 53 will do.
This does a heap put. Oh, this has a bind as well. Okay. bind address age. Yeah, this is basically a set variable, but with this bind here, actually.
Well, we can copy paste it from there, but to me it's fine.
Here. Uh, if the
Yeah, just
derived cell
oh,
is an address, we let computer equals bind takes a computer, right?
it does.
It does uh, set value, set variable takes a register, which is going to be the A register. Yeah, I need to do the set variable first and then the bind. And that should be enough, I think.
That's wait. Can you go back to the book?
Set here.
The is bind. Oh, is bind interacting with the heap?
Is bind interacting with the heap? Um,
Well, let's go to the code.
is bind interacting with the heap?
Let's just go to the code. It's there.
It will be actually.
No, so then you can't do what you said.
Bind address with the age. Hmm. Yeah, this is mildly annoying.
No, just copy paste the variable and add a bind. It's that easy. And then later we can make a generic function that accepts an arbitrary lambda or something. And then we can do what you wanted.
Let. Uh, how do I do this?
What do you want to do?
I need the age register.
That's it.
No, that's just it. Uh, we don't care about everything else. Equals computer in.
No, you actually care about the
Actually,
store.
I care about the store as well.
Yeah, so you do let reference, remove the H register, put the address. Oh no, sorry. It is H register. I said bullshit. It is H register. Then you do the store heap put, and then you need to
Then
call
we do
bind.
the bind with the address and the age register.
Ah, that sucks. This returns a computer friend. And I don't know
And
if this is in
this,
scope. This may be down there. So that it's not in scope yet to be used.
well, actually, if that's the problem, computer with store.
You can replace computer with the bind call if you want.
But that's going to override the store. That's not what I want, actually.
Wait, you don't want the bind to use the updated store?
Here,
That doesn't make sense. Why don't you want the bind to use the updated store?
because we're updating the store here,
Which is
we need
before
we
bind.
need we need this store to be before the bind, which means it needs to be here. Although, is it a problem if we bump the age register? Does bind use the age register? I don't think it does.
No.
It
It doesn't.
doesn't.
It doesn't.
So this is actually fine. And then we're doing set register register. It's coming from.
Yeah, and then we are using the reference, the same reference. Yeah, this is
Yeah,
correct.
this needs to be DA register though.
Yes, that's true. And that's it for put unsafe value implementation. I have no clue if this hack is going to work, but I'm trusting your intuition, brother.
Uh, it's not Q. There was a halt in the debugger.
Are you sure? I think we're calling it trace instead. Wait, what do you want to do with halt?
I want to just exit.
Then it's trace.
Trace. No, this is to turn off the instruction tracing.
Oh, you want to kill the program?
This leaves the debugger, but there's no halt actually.
Let's
Well, we
put
can always
introduce
let's just
k for
fail.
q.
Let's just fail.
Okay. You can introduce k for q and just return the. Uh,
Oh right, you saw the halt and you replaced it with help, but it's a to do.
yeah, yeah, but
Yeah, this.
halt is not returning the computer though. You want to kill the program. This is not halt.
Yes, this is halt.
No, it isn't. This
It
is
is, and I can prove you. I can prove it. Oh,
okay.
unbound type constructor address.
Oh, okay. So you need to put the definition of the alias above, all the way up. Same thing for the ref. Need to put all the way above.
Here. See, if I say, yeah, now it says halt. See, if I just say halt, that exits.
Oh, so we do have the QA program. Okay, my bad then.
I think I'm gonna keep this like this actually.
That's a little inconvenient, but okay.
I mean, it's not often that we wanna halt, and we're only going to be able to do it once for each run, right?
Sure.
Uh, right, we need to go to main and
No, no, no. Let's see if this the. Well, actually, no. You can change this. This was just to see if the unsafeness was going on. Well, which it is. But I'm a little bit. I'm not optimistic about this. Well, after tail calls, it fails really fast. So let's go.
set option buffer file type prolog. There we go. So we hit the first debug after calling triangle 2. And actually, let's just go.
Same place,
We're
same error.
still failing in the same place actually.
Same place.
Uh, Memory and stack. Put value on x2. Put structure. There's another new there. Put value. Oh, that's register to register. Deallocate. Execute triangle 3. Try me else. And we have a bunch of addresses, that's fine. And we have a bunch of addresses and that's fine. Is it fine?
Someone is mentioning address 400, man. I don't think
Um,
I've never seen that before.
That's in the trail, I think.
Okay.
Uh, we have the internal registers, right? Printing somewhere
Yeah,
here.
X.
Oh no, it's R actually.
Uh, what is the difference between internal registers and? Ah, no. Okay, I do remember this.
PCP, B, H, and HB are both 105. They are both 105 and B is 200. Okay, B is 200, that's correct. Oh, you know what it is actually? B is greater than E, right? Unreachable get structure.
Yeah, it's 130. We don't have a reference inside the get register, essentially.
We have a structure instead.
Yeah,
Well, if we have a structure instead, technically,
that doesn't make sense, right?
no, it does actually.
How come? No, but that's not the same thing. That's not the same thing, Marinho. Having a structure is on the second pattern matching, not on the first.
Well, it can happen in both actually, since we now have structures in X registers, Y registers as well, I guess.
Ah, I see what you're saying, actually.
Put value, deallocate, execute, try me else, allocate, get structure. Yeah, that doesn't break anymore. And what's the stack like?
Wait, you literally copy pasted?
Well, it's the same case. It's just here it reached
That's
this case by,
hilarious.
well, yes, because here we reach this case after we go through a chain of references. But here is like, okay, we just have a structure in the X register. So let's just deal with it.
That's funny. Okay, let's continue then.
Structure. You know, I think we may actually be able to get away with doing a tail call here.
Of course, that's what you're looking for, right, buddy?
Because then, if we do that, do we reference the adder in any place? We don't. So yeah, we can just do that because
Wait, what do you mean by doing a tail call? Do you mean in OCaml or in the compiler?
I mean, this get structure, uh, functor label, functor arity, then register, except get register register computer. That doesn't quite work though. That does not quite work. That's kind of sad actually.
That's actually gonna be like the same thing, right? We're gonna just loop over. Oh, you wanted to call itself, so then it will go to the internal structure on 118. Oh,
No, I
I
wanted
had the
to call
opposite, right?
itself
You
so
want to
we can
call.
hit the altar.
Yeah,
Yeah.
yeah. I see what you're doing. I see. Actually, there is a way to
Yeah.
do it. There is a way to do it. You want to tell me why? How to do it?
How do you do it?
You do a set register on a register using the structure on 118, and then you tail call on it.
Uh, that has a side effect on the register content. Is that a problem?
Yeah, I agree. It has some side effect.
Let's just keep it as it is for now.
Yeah, we can. Like, I don't have problems with copy pasted code right now.
Uh, let's just go. So we do unify variable. What about the stack? We don't have any references to the stack itself. What about the memory, the heap? This seems okay so far. Where are we in the program? We are in a call to debug after doing get variable. I think this is after the plus, possibly. No, this is the debug here, actually. Okay, so get
Yes.
structure, successor one, unify variable y2.
Yeah, this was already happening before. There will be a get structure that will fuck us over.
0 is structured to 101, which is the original argument. X2 is structure 104, which is new. Let's just skip over the plus actually. Plus 3, try me else. Get variable, get structure is failing. Actually, the get value is failing. Unreachable get value. I
Which an
think we have the same
unreachable.
problem there.
No. Get value just calls. Wait. Just calls unify. I am confused. Search for unreachable get value. What the fuck?
Oh yeah, it's literally the same problem. You see?
Okay, so what do you plan to do here?
This is calling get value with the addresses, right? Which is
Oh,
just unify.
yeah, because that's what unify expects, just the numbers. Wait. In there we can have structures now. Is that what you're saying?
Actually,
That's weird.
can unify handle the new heap layout?
No, this is the latest unify. Like this does. It should be doing all of it. I am still confused. What does it mean a get value to do stuff with registers, with structures?
Well, a structure is kinda like a reference, except it's already bound to something we know to be a structure.
Okay, and you want to change the unify instead of changing the get value down there.
I'm not sure. I'm looking at Unify to see if it even makes sense to change it, actually. We have two addresses. We call the loop with the prepared computer, which pushes stuff to the PDL. I think this might be assuming those addresses point to references, maybe.
Now let's read. Unify definition. Let me just read the get value definition. Get value. Unify variable and register, backtrack on failure. That's the definition of get value.
We do store gets if they are both structures. If they are both structures.
Oh, but if they are both, yeah, we're not gonna hit here, right? Because it's on the unreachable down there. We're not calling unify.
And if they are both functors, this is not gonna quite work though.
But again, can we go back to the question? I didn't quite get it, and I'm sorry, but it's quite late. What does it mean to do get values on structures?
What does it mean? It's the same as doing a get value reference, except those two structures, they will only ever unify if they are like they are already kind of bound in a way. It's just we know ahead of time that they are structures instead of references.
Yeah, but how do you unify them if they are structs?
Mm,
Because that's essentially the semantics that you want to introduce here, right?
I think we may be able to get away with just removing this match and pulling this functor case up here and getting rid of this, but this has the problem that actually is it a problem?
Well, it is a problem because this pattern match on line 179, this is assuming that we are we are already dereferenced the shit out of it, right? We are already in like un undereferenceable thingies. That's the assumption that we are making via 179.
Uh, yeah, actually this is safe.
Okay, I'm a little bit surprised because we know we have structs in there, but I'm liking your boldness today, Marie. Line 180 is complaining about something.
180.
Yeah, it's red in there. Oh,
No, it's not.
now it's not. So you know we're never gonna get structures in there.
Yeah, because we don't put structures like this directly on the heap anymore.
Okay, so let's change the get value, right? Oh man, we're gonna have to change the colors of Unify everywhere else as well. That's kind of sucks. You see the problem?
The colors of
Unify.
Unify.
Yeah, because you want to change the signature of this, right?
No,
Instead of
I don't.
no, you need to because otherwise we're gonna reach the unreachable again.
How?
No, just go to the pattern matching there. Unreachable get value. Let me take a while. Yeah, we know that this fails, right? That's how you got to the unreachable. And that is happening before you call unify on 155.580 anyway. No, you're gonna have to do all the other cases as well, no?
Yes, I am.
Okay, that kind of sucks. What about structure with structure? Is that possible?
It is.
Yeah, that makes sense. You added an extra comma in there.
I added an extra comma. You are correct.
I wonder what the formatter will say about this. Oh, okay. I was expecting much worse.
Reference, reference, structure, reference, reference, structure, structure, structure.
I think there's a neater way of doing this. You want to know why? How?
How?
I think that between the commas, you can actually do another OR pattern with parentheses. You see what I'm talking about?
Between the commas.
Yeah, so in 556, instead of doing reference, XADDR, and then comma, you do parentheses before the reference, and then after XADDR, you do pipe, structure, XADDR. Well, I was talking about putting the pipe inside the parentheses, but let's see.
Like this?
Yeah. Damn! That actually works! Boom. Huh?
Yeah, this is nicer.
Damn, let's try. Let's try it out. My Nathan told me about this trick before when we were implementing spatula.
Where did we break before? It was when we called +3. +3?
We didn't fail
Yeah,
this
that
time.
worked.
And now we do.
Unreachable the ref cell.
Unreachable deref cell. And this is an output value, brother. Which means that
Yeah, this is new. That means
unreachable
we got
is.
something that's neither a reference nor a structure though.
What could it be? A functor?
Well, that would be an error if that's the case.
Shouldn't we print it
Actually,
in there?
yeah, this is happening. We call plus, try me else, get variable, get structure, get value, proceed, debug on 19. This is this
Mm.
debug. And then we failed while setting up the arguments for this call.
And we call on the new stuff on the other gamble move.
Let's see, what are the X registers and the stack?
The shit sounds
Oh,
loads of stuff in the stack.
yeah, this shouldn't be here.
Oh, we have a functor inside the stack.
Yeah, that shouldn't be there.
Who is doing bullshit?
Mm,
We are doing a bunch of put values, man. Isn't the put values doing bullshit?
this is a functor with a successor 1. Actually, let's halt and go again. Skip 1. The stack is okay. The stack is still okay. Still okay. Still okay. Reference to 214.
Yeah, this is an unbounded already.
Is that an issue?
You're
Maybe.
you're
Maybe not.
referencing the heap here. Is that correct?
Call plus? What do you mean?
When you ask for the stack, we have heap addresses in there. I
Well,
think
yes,
that
because the
I
the
think the
stack.
rule that we read is that the heap can't reference the stack, right?
Yes, the stack can always reference the heap.
Okay, so never mind.
Try me else.
It's still no functor.
Get variable. Get structure new.
Let's
Get
get it.
value.
Yes, get value is doing the bullshit. Here there it is. 214.
Yeah, there's a problem in the unification now.
Yeah, we changed a significant thing.
There's a
We
problem in the unification now, and the problem actually is.
I have a question for you.
Yes.
No, actually I answered my question because you swapped V1s and V2s with D1s and D2s on
Yes, I did.
193, right?
But actually, yeah, no, the problem is related to this. It's just. Um,
Oh wait, we didn't go there. It's not what you said. Because if we had, we would print line 191. The fact that we have a functor and the problem is unification. That means that 182 didn't match, right? Or the if on 184. 184 actually, most probably. We got functors, but we didn't. Or hear me out. 199 now is also a possibility. Maybe we got something different.
but those
And
are failures, Lemos.
oh, those are failures on the backtracking side. That's not failure of the program.
Oh, yes, but if we backtrack, that means we unwind the stack. Unify loop. We printed this.
Yeah. Then we printed PDL empty somewhere, and we didn't print the loop there or the fold. Sorry, on 191.
Oh, I think the problem is the bind now, actually. Yeah, the problem is definitely the bind.
What is the problem? Oh, they use references ifs maybe.
No. The problem is we do a get store, we check if they are references, etc. The problem is those puts, actually.
What do you mean,
Um,
brother?
we need to do something like this. Match with If this is a functor, then actually we need to return the structure of A1.
Man, I'm so impressed how you're freestyling this today. So impressed.
Otherwise, we need to just return the value. And we need to do the same thing down here.
Well, we can make an auxiliary function for this later. It doesn't matter. Look at this hack. Holy fuck.
Okay, the formatter wants to put the line. I think that's fine, actually.
Yeah, that's fine. Can you explain to me why? Why in a bind, if we have stuff that are functors, we should convert them back?
What happens if A is the address of a structure?
Then we need to unify the stuff with the structure.
No. If A is the address of a structure, it's going to point to a functor. But a functor is meant to be the header of a structure. It's not a reference, so it shouldn't be in a register.
Oh, the number that the structure is holding is the address of a functor. That's what you're saying.
Yeah, like if we try to do a bind and this A1 originally came from a structure of whatever, it's going to point to a functor on the heap. And if that's the case, then actually this should be a structure of the original address, not the functor, because that's not the information we want.
That makes sense. That makes sense. But I'm still. I'm not gonna rant. Let's go. Let's see if that fixed itself. It's after I get value though. Let's pay attention to get values.
Uh, this is after executing 43. 43, yeah.
There's
Yeah, there
no
we go.
functor. It's a structure 105. Let's see the heap.
105, which is the successor, yes. Which is a successor. That's
Jesus.
correct.
Okay, let's continue.
Proceed.
Which debug
Then
is
we
this
are.
one? Wait. Can you go back to the program?
This is just after the plus.
Okay, so we are on there. We are preparing to call triangle, I guess, now.
Yes, we're preparing to do the recursive
Which is the
tail
problem.
call.
Which is the problem. This is where the problem was happening before. Yeah, only arg counts addresses, references, and structs. We don't have functors in here.
We have a reference to 214. Is that a problem?
We have a reference to 214.
It isn't because of backtracking. Okay.
Ah, okay. Interesting.
Okay. But actually, yeah. So x0 is 215, and 215.
Is a reference. It's an unbounded thing.
Yeah, we're gonna have the same problem we were having earlier.
Really? You can already tell.
Because this is a free variable, Lemos.
No, I noticed that, but I don't know the next instruction. We haven't called it yet though. So let's continue. We're just preparing to call it.
Wait, why is this a put variable? This should be a put value, actually.
Now is a code generation problem. This is happening.
It's not programs code. We were in address 20. Yeah, this is a put variable y2.
And
And
this is
if we
after you call
print the
plus.
If we print the functors, this starts at address 6. So try me else allocate get structure unify variable y2. This is correct because this is the first occurrence of y2. Get variable, instruction debug, put structure successor, set value y2 is correct. Put value, put variable y1. But actually that's fine because y1 is x2, which is... No, wait. Oh no, this is preparing to call plus, so this is the new accumulator, so this is actually correct. And then we do put variable y2. When this was already a unified variable up here, this should be a put value, that's the problem. This instruction is wrong.
Wait, imagine that was the problem all along. But that was not true before, right? What happened? We didn't have this problem before, or did we? And we just get didn't get it in time. This is called generation problem, right? This is it. This is the only place. Allocate body. We do inside allocate argument.
Mm,
Hello?
I heard the notification sound.
Ah, okay.
That's fine.
This is the only put variable in this file. No. No,
Those are
actually
in
yes.
machine and evaluator. Yeah, this is the only one.
Okay, so whatever we're doing, we are not finding the stuff. Why are we not finding the stuff? That's weird.
Hmm.
Are you sure this should be a put variable though?
This
A
should be a
put
put
value,
value.
sorry.
It should, because this is in the body of triangle 3, the first body, I should say.
Could you go back to the
And
example, please?
go back to the example. Triangular.
This is we're preparing to call triangle, right? Is this
We're,
what we're doing?
yes, we're setting up this argument in particular.
And we are putting y2 with put variable.
Which is wrong, because this variable already appeared twice.
No, but if it appeared twice, it should be in a y register, right?
No, that's not the problem. The problem is that it appeared twice, which means it was already set up with unified variable, which means it should only ever see put values and unify values after that.
Makes sense to me. Makes sense. So the question
That's
is now the following. What are we doing it wrong? Well, I guess the scoped variables map is fucked. That must be the case, right? That must be true.
that must be the case, yes.
Because if you go there, we're doing a find opt on the scope registers with the raw register. And we are getting none for some reason. Which is weird. Why?
This comes from the generator, which comes from here. And this generator comes from here, which comes from here, which is the argument to allocate body. Hmm.
Yeah, so the scope registers, they are not doing their thing impressively. I wonder why. Maybe you are resetting the scope registers incorrectly. Maybe, but that's
Maybe.
so weird because that means that we are not adding it the first time properly.
But we must be because we are using a set value here.
Does the set value put stuff into the scope registers?
This is put variable, this is put value. This is add instruction.
Actually, let me change my question. When should we add stuff to the scope registers? The scope register
Uh,
is a new thing, by the way. There's a solid
when,
chance you're missing a place.
whenever we, like the very first time that we emit an instruction that prepares a variable, we should use the variable variant of the instruction. So unify variable, put variable, get variable,
No, 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 no.
those.
I
And when
remember
we
that.
do that, we need to add that variable to the scope register so that next time we use the value variant instead.
Yeah, no, but we are doing that on 249, as you can see. 249 does that, right? Which, by the way, your grep is only grabbing these six occurrences.
Those are the only ones in this particular
So we're
scope, yes.
definitely fucked because you're not resetting it. We need to reset this.
This is reset whenever we allocate a new body, actually.
I don't follow. Who is resetting it? Who is doing scope registers equal empty map?
Mm,
Oh, 24. No, no, but that's just initialize. Keep going. Keep going.
this is emit argument. This is coming from up there. This is also coming from up there. Find opt.
This is the place that we are doing the. This is the problem. Yeah, man, we are never resetting the scope registers.
Hmm.
We are never resetting the fucking scope registers. Where are you resetting the variables? Should they be close to each other?
Where are we resetting the variables? I think they are being reset in each declaration body.
Should we the should we reset the scope registers in each declaration as well?
Well, if we are resetting in each declaration body, then we, by implication, are also resetting in each declaration because each declaration has at least.
Okay, so we should reset on each declaration. That's what you're saying?
Yes.
Are we doing that? Can you check the compiler.ml? Because maybe
Generate declaration and patch.
that's not it. This is not where we reset it. We have a function called reset up there.
Generate single declaration.
Reset variables. 326.
Yeah. We reset at the end of this, and we also reset at the end of this.
Should we do the same with...
We call initialize with the p register,
Oh, so we're
which
already
gives us.
doing that actually, by
Yes.
accident.
No, no, no. This is definitely intentional. It's just that, well, it's not obvious where it's happening.
Yeah, the name is bad. It's not only resetting the variables anymore. Well, I guess the variables of the code generator. Well, it doesn't matter. So, okay, but we are doing this. That's good. That's good. But I have a feeling that we are not doing an add on the scope registers properly somewhere. You know why? Because the find didn't happen here, right? The find
Mm,
just didn't happen.
emit argument. Is this emit argument?
Yeah, this is just doing get variable and get value. And for some random reason, we are adding to the scope registers. Are we? Oh, we are 141. Okay, that's bad. Which places should be adding stuff? That's kind of my. For example, in the set value, are we adding to the registers?
In the set value.
Yes, somewhere we're doing a set value, right?
This is emit argument. Variable value catch all.
There we go. This is not adding it to the scope registers.
Well, it should already be there if we are in this branch though.
What do you mean? No, no, not this branch. I'm talking that in here we are changing the variables map on 181, but we are not
Yes.
changing the scope registers. Is that a problem?
Mm. What is the difference between scope registers and variables though?
I have no recollection anymore of the difference. We made this really recently. Really, really fucking recently. Well, the difference is what they are holding. One is holding variables and the other one is holding registers, which is not the same thing. I think they are holding the registers that we already have been used during this predicate.
Hmm.
I think that's what we're doing with it. Well, but that kind of makes sense because I remember having a discussion with you about the difference between put variable and put value was not on the level of variables. It was on the level of registers for some reason.
That's because registers are the low level representation, well, they are a low level representation of variables.
Well, but I don't remember anything else after that. So if we were crazy or if we were geniuses, I can't tell you. The question is, do we need to rely on how can I say? What are you doing, brother?
Undoing a move. Yeah.
That will not. But that wouldn't change anything. Yeah, but do you think we need the scope registers now, or do you think we just need the variables?
We have to review that actually, because I don't recall.
I don't recall.
Um, I think this is a good stopping point actually. Let me just write a to do here so we don't forget what we're doing.
Add a to
Where
do
should I?
about the put variable. Put in the code generation, man. Put in the code generation. Yeah, there must be. there's something wrong about the put value and put variable nonsense. And the rationale is someone is not adding stuff to scope registers. I'm gonna bet on that place that you were of the set value. There we need to also to record the register. Don't you want to do that right now, man? Because it's really easy to change that.
Where?
Go grep for set value. These only two cases in the file. Perfect. Then on the let on 179, you're gonna add another one, which is the scope registers. You're gonna actually have like scope registers, comma, everything else. And then on the none, you're gonna do s add regist lm, I think lm to the scope registers. See if that compiles.
And
That
we need
doesn't
to
com
grab
that doesn't compile.
the.
I think it's register maybe, not not
No, no, no. We
lm,
need. No,
not
no. We
lm.
need to. We need to grab the the scope registers actually from here.
Yeah, exactly. Yeah, but this is still wrong. Uh, yeah, lm is what? Is a key. Yeah, this is nonsense. Put register in here.
Nope.
What is it still complaining? I am confused. What the fuck is complaining?
This expression has type. Um, Cell register is not compatible with register allocator register. It's a cell register, not a register allocator register. Why do we have two register types in here?
I have no clue. But let's fix that. That should be very easy. So find a place where you're gonna do the opposite. Okay.
Yep.
Okay. I see some cocoon magic in here.
Uh, uh,
Okay. The type signature is fucked though.
there we
There we
go.
go. Okay. So now apply this function down there.
Apply this function down there. Not here, here.
Yeah, so now you change register using your function. You need parentheses on that stuff. This should be it to my theory. Yeah, let's try. Let's run it and see the code. See.
Um, this was right before we did the execute, right?
I have no idea.
Yeah, right here. Execute triangle. Put value, but everything is now temporary. That's not correct at all.
Wait, everything is temporary. We don't have put variables anymore? Is that what you say?
Try me out, allocate, blah blah blah, unify variable y2, get variable y0.
No, there is a put variable happening on 17, for example.
Put variable y1 plus. Wait,
Oh,
put
it's still.
variable
Yeah,
y1.
yeah, but it's still fucked on line 20. It's still doing put variable on y2 on y2. It's still fucked.
Put variable y1. Oh, that's the new accumulator. That's correct. But put variable y2 is definitely wrong.
Yeah, but that didn't change anything on the 20. You see, It's y
Yeah.
choose x0 put variable still. Oh, wait a moment though. There is a put value immediately after. No, no, no. Oh, that's not a no op. That's not a no op. Yeah, that's fucked. Yeah, just Control Z this.
Actually, this is flipped.
That's also true. See?
Code.
20. Immediately go to 20. Put variable. It's still fucked. Put variable on y true.
Yeah, this is still wrong.
Yeah, they didn't change anything. But we discovered something. We discovered that there was some unsafeness going on about the put values, and then you had a crazy idea, a crazy insight that you can combine the put value with the put unsafe value.
I mean, if you just always use the unsafe version, that's less efficient, but it shouldn't be wrong semantically.
And we also identified that there is something on the code generation that is significantly wrong. This is progress. Yeah, I would recommend you to undo my changes though, the changes that we just did in the code generation.
I'm not gonna commit those, actually. I'm just going
Yeah,
to,
I'm gonna
first of
finish the
all,
recording now.
okay.